cost-sensitive learning, Charles Elkin, an overview of the analysis of that paper on cost-sensitive learning by Group 4. The background for the paper will be presented along with some of the ideas. Cost sensitivity is one of the fundamental ideas. The way we go about making an optimal decision by thinking about everything in terms of cost. Then some practical approaches in implementing the ideas of incorporating cost into your standard classification learning algorithms. We will present some recommendation and conclusion. Now, standard classification algorithms basically they function by maximizing accuracy. They would like to get everything perfect. In this world, we are living in situations where we need to ensure that if we are not certain about something, then we need to make decisions that are actually the best optimal decision that will be of less cost. The situation is shown in our example of, well, we have a biometric scanner operating as the lock for the door, and within this biometric system there is a classifier. What happens when the classifier learns the faces or the fingerprints of the family members? The classifier definitely would be able to detect family member and open the door for them. When the classifier rejects or does not recognize the family member, then the classifier does not open the door. The family member may get annoyed. Now this little idea is the cost. But what happens when a stranger, robber for example, gets to the classifier and the algorithm classifies that thief as part of the family member and opens the door? We have what we consider to be a greater impact of the cost in this situation. Now, Elkan's paper dives directly into this situation, this real life application situation. He gives us ideas of cost sensitivity, cost sensitive learning, how we could incorporate a cost by the costing matrix, how we could get probability thresholds and incorporate that directly into the classical learning algorithms. Now this is the general idea of his paper, and then he puts together fundamental conclusion that shows us even though we try to apply one method, this method may or may not work. Now, let's look at what cost-sensitive learning is. The essence of cost-sensitive learning is, or cost-sensitive decision-making, is that it can be optimal to act as one class, even though your probability estimates make you behave or look more probable, even though when some other class is more probable than this class. Now, how is that achieved? From equation 1 in the paper, we call it the costing policy equation. It gives an idea that we need to incorporate a cost, which we will sooner or later show as a costing table, values of a cost along with our probability estimates to make those optimized decisions. So when we look at our old algorithms or the normal classifiers, they are maximized in accuracy. When we incorporate cost, we are trying to optimize our decision. And the important step at this point in the paper is that we need what is called a cost matrix. And so Tua will now give us an idea of cost matrix.
Hi, I'm here to talk about the cost matrix and cost versus benefit. This is the structure of the cost matrix C when there are two classes. And this one is the cost of false negative, and this is the cost of the false positive. The cost of labeling the examples incorrectly should be greater than labeling the examples correctly. These conditions called reasonableness conditions. suppose that the first reasonable condition is violated. For example, if 0, 0 greater than or equal to C10, but still C01 greater than C11, then the optimal policy is to label all examples positive. If 011 greater than or equal to C10, but still C01, but still C10 greater than C00, then optimal policy is to label all examples negative. Now look at the cost versus benefit part. Although most recent research in machine learning has used the terminology of cost, doing accounting in terms of benefits is generally preferable, because avoiding mistakes is easier since there is a natural baseline from which to measure all benefits, whether positive or negative. Baseline is the state of agent before it takes a decision regarding an example. After the decision is made, if it's better off, then its benefit is positive, and otherwise its benefit is negative. Now look at the examples of credit card transaction. This column refers to benefit and this column refers to cost. It's rational not to approve a fraudulent credit card transaction can prevent fraud and lead to arresting a criminal more by benefit than cost. It's rational not to approve a large credit card transaction even if the transaction is most likely legitimate. That's more cost than benefit. Next is James is to talk about optimal decisions. Thank you.
Thanks, Tuva. In Alcon's paper, he showed us that equation 1, as explained by my teammates earlier, is the equation that needs to be minimized. The value that in this equation needs to be minimized, that is the cost of predicting a certain outcome. So we can see that classifiers make predictions based on a probability threshold P0, like in standard non-cost sensitive classifiers. And how do we link these two concepts together? You know, from cost base and the standard classifiers that are non-cost sensitive. Okay, eventually we'll see that we'll be able to derive a specific probability value that's the new threshold for making the prediction decision. Based on cost, we can see that there is a certain cost for predicting class 1, and there is a certain cost for predicting class 0. And it is it makes sense that we only make a decision that the prediction should be class 1 if the cost of predicting class 1 is less than the cost of predicting class 0. And if we assume in this statement here, if we assume that if we let P probability of the example being class 1, the true class is 1 as P, and then the probability of the true class being 0 will be just 1 minus P. And simplifying this statement here, we get a specific P probability value expressed as the formula of the cost coefficients, and we now can make predictions that are cost sensitive if probability is for class 1 is greater than P star, then the optimal decision is to make class 1 the predicted class. Practical methods for achieving cost sensitive predictions. There are different ways of implementing this. One way is to actually change the algorithm itself to build in the cost sensitivity. Other ways are to do pre-processing or post-processing without really touching on the algorithm for calculating the probabilities. I'd like to then pass on to my teammate to explain how these classifiers can be made to learn to make decisions on the cost-based probability.
Thank you, James. So our main question at this point, we have understood that there is a way to incorporate cost into our decision-making system. Now, our main question is, how can these classifiers, the naive-based decision tree, how can they be made to learn the decision or to make those decisions based upon this general probability that was established by James, the P-star probability? Now, Danushka will give us the two ways that are proposed in the paper by Charles, by Helga and Charles. Thank you.
Thank you. In this next part, we will see how can classifiers be made to actually make decisions based on a more general probability value or based on the threshold value. The author discusses how cost sensitivity is achieved by rebalancing. Rebalancing is the process of changing the proportion of positive and negative trading examples in the trading set. And he proposes two methods. Basically, one is non-sampling and the other one is sampling. And under the non-sampling method, he uses weights, and under the sampling method, obviously, he uses sampling. So, when you talk about a weight, what happens is you have a number of negative examples in a trading set, and this is multiplied by a formula which is given by the first theorem here, and we talk about the first threshold, which is P star, what James was talking about earlier, and this is the first method that is proposed. So you have a classifier that uses weights, and using this probability threshold formula of the equation, it needs to multiply the weights to find them. Moving on, we go on to the sampling methods, which the author has briefly described. Sampling can be done randomly or deterministically, and the two methods are oversampling, which is actually duplicating examples in the training set, and the other method is undersampling, which is done by deleting the examples. Now, what both this actually does, it changes the data, it changes the training set and the data, and there are changes to the population and hence the base rate. Okay. So now, using these new base rates, the authors then investigate whether changing the training set causes changes in the base rates, and that is expressed by the theorem that you see here, which comprises of P, which is the probability on one set, and then P dash being B dash being the base rate on one set is B, and B dash is the base rate on the changed training set. Right? But however, the question remains, and that will be discussed in the conclusion, whether this actually helps to make optimal decisions. As sort of like a byproduct of this, what has happened is, because we are using two different training sets, this removes the unique dependence for machine learning training algorithms where, for example, the classifier used a training set and a test set from the same probabilistic distribution, as you can see here. And because of this new theorem that we just saw, the classifier have the ability to now learn the training set from one set of probability distribution and test set from a second different set of probability distribution. This is a unique feature that the authors have also discussed in this. General feedback about the article. This is obviously very non-trivial and it's significant in this field. It covers a very novel approach, and which is actually coming into prominence with big data and prediction and all that. Currently, this is coming into mainstream, where you incorporate cost of decision making into an algorithm so that you make optimal decisions. The article has been cited 850 times in Google Scholar, obviously showing how important it is in the field of machine learning. As something missing, maybe when we were doing our research, we found out that other methods were not discussed in this paper, including post-processes and post-processes using outputs from the classifier, which are then modified to make optimal decisions. So this is something that we didn't see in this article. Finally, the conclusion, I think this was a very good review for how optimum decisions are made in the presence of misclassification errors. We also saw balancing, how the author discussed of how balancing the positives and the negatives. It was discussed and it was shown that it does not is not very effective in making optimal decisions. The changes in the base rates and the frequency of the class that you're actually looking to predict, the change of that has no influence on the net classifier. That was demonstrated by using naive Bayes in the last chapter of the article. However, what he does recommend is that better results can be obtained for the two classifiers of Bayesian and decision trees by learning the classifier on the data as given at the given data set, and then using equation 1 after smoothing probabilistic output. Now, equation 1, if you remember, is the cost impact on the learning, and also equation 2, the one that we started off this section with, rather my section with, is using a threshold probability and altering the threshold values of the classifier. So these are the recommended methods, and these are the references that we have, and that brings us to the end of the presentation. Thank you.